Head-on elastic collision. A head-on elastic collision is a one-dimensional collision. The velocities of the objects involved in the collision are all lined up along the same line, and that is true before and after the collision. Notice also that in this collision, the mass m2 must be at rest before the collision. Elastic collisions are those collisions where the energy is conserved. The algebraic derivation of the final velocities for mass 1 and mass 2 are a little bit challenging, and I would like you to be patient and very attentive. Since the net force is equal to 0 during this collision, therefore the momentum is conserved. The momentum initial equals the momentum final. The momentum initial comes from two masses, m1 and m2, m1 times v1 plus m2 times v2. The two masses after the collision are going to have different momenta. The momentum for mass m1 is equal to m1 v1 final, and the momentum for mass 2 is going to be m2 v2 final. Since this collision is one-dimensional and we have an x component only, m1 v1 has a positive component, m2 v2 is 0 because the mass m2 is initially at rest. After the collision, the mass m1 is going to have a momentum equal m1 v1 final. We don't want to predict the sign of the vector momentum after the collision. The algebraic formulas that we're going to derive will predict that for us. The mass m2, of course, is going to move forward and is going to have a positive momentum, m2 v2 final. In order to make the solution easier for me later on, I am going to bring the like terms together in this equation. In other words, move m1 v1 final to the left-hand side of the equation. The result is m1 v1 minus m1 v1 final is going to equal m2 v2 final. The next thing I need to do is factorize the m1. m1 times v1 minus v1 final, that's going to equal m2 v2 final. Isolate the v2 final. By dividing both sides of the equation by m2, you obtain m1 over m2 times v1 minus v1 final. Clearly, this equation includes two unknown variables, v1 final and v2 final. For that reason, we need another equation to be able to solve the question. The other equation can be obtained using the conservation of energy because this collision is an elastic collision. The kinetic energy before the collision must equal the kinetic energy after the collision. The kinetic energy before the collision is coming from two parts, m1, which has a kinetic energy equal 1/2 m1 v1 squared. The kinetic energy for m2 is 0 because the mass m2 is initially at rest. That's going to equal the kinetic energy for m1, which is 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. You can cancel the halves between all the terms. Like we did before, let's move the like terms to one side of the equation. m1 v1 squared minus m1 v1 final squared equals m2 v2 final squared. Like we did before, let's factorize m1 on the left-hand side of the equation. It becomes m1 times v1 squared minus v1 final squared. That is going to equal m2 times v2 final squared. Now divide both sides of the expression by m2. You get m1 over m2 times v1 squared minus v1 final squared equals v2 final squared. Notice that this part of the equation, which is the difference between the squares, can be factorized as follows. Remember that the expression of a squared minus b squared is equal to a minus b times a plus b. This is a famous expression that we have learned early on in algebra. As a result, this expression can be simplified further. m1 over m2 times v1 minus v1 final times v1 plus v1 final. That is going to equal v2 final squared, which I am going to substitute it by the expression that I have found earlier. m1 over m2, make sure to square it because the expression is in squared form, times v1 minus v1 final squared also. Now let's try to simplify this expression a little bit more. The v1 minus v1 final, this term here, can cancel with the square because that expression is the same, v1 minus v1 final. In a similar way, the m1 over m2 can cancel with the square here also. The simplified expression has the following form: v1 plus v1 final equals m1 over m2 times v1 minus v1 final. Notice that this expression has only one unknown variable, which is the v1 final. Let's try to isolate it. First, multiply both sides of the equation by m2. The expression becomes m2 times v1 plus m2 times v1 final equal, distribute the m1 here, it becomes m1 times v1 minus m1 times v1 final. Now let's move the like terms to one side of the equation. The v1 final, we're going to move it to the left hand side, and the v1 terms, we're going to move them to the right hand side. As a result, you obtain m1 v1 final plus m2 v1 final. That is going to equal m1 v1 minus m2 v1. Now let's factorize v1 final from the left hand side terms. v1 final times m1 plus m2. Factorize here the v1 from the right hand side terms. It becomes v1 times m1 minus m2. Divide both sides of the equation by m1 plus m2. You obtain the following expression: v1 final equals m1 minus m2 times v1, I just moved the v1 to the right hand side, divided by m1 plus m2. To be able to solve for the v2 final, you need to substitute the v1 final that we have obtained here in the previous equation that we have been able to derive, which is the following one. The v2 final equals m1 over m2 times v1 minus the v1 final, which I am going to substitute by this entire expression, which is m1 minus m2 times v1 over m1 plus m2. Now let's bring the terms inside the parentheses to the same common denominator. The expression becomes v2 final equals m1 over m2 times m1 plus m2 times v1 divided by m1 plus m2 minus m1 minus m2 divided by m1 plus m2 times v1, close the outside parenthesis. Now let's simplify this expression further. v2 final equals m1 over m2, m1 times v1 plus m2 times v1. Now let's distribute this negative sign over the second term. It becomes negative m1 v1. Negative times negative, that's positive m2 v1 divided by m1 plus m2. Notice that m1 v1 minus m1 v1 becomes 0, and m2 v1 plus m2 v1 is 2 times m2 v1. Therefore, v2 final equals m1 over m2. The term left in the numerator is 2 times m2 v1 divided by m1 plus m2. This m2 cancel with this m2, and the final expression for v2 final is going to be 2 times m1 v1 divided by m1 plus m2. Clearly, from the expression, the velocity v2 final at all times is going to be positive, which means that the mass m2 is always going to move forward after the collision. However, the mass m1 is the one that needs some explanation. Looking at the expression for v1 final, we notice that the numerator has the expression of m1 minus m2, which means if the masses m1 and m2 are equal, the v1 final is going to equal 0, which makes the mass m1 to come to a perfect rest after the collision. If m1 is larger than m2, in that case, the v1 final is going to end up to be positive. Therefore, the mass m1 after the collision is going to move forward. Finally, when the mass m2 now is larger than the mass m1, in this case, the quantity becomes negative and the velocity v1 final is going to be pointing towards the left, which makes the mass m1 to bounce back and move in the backward direction. All of these situations are going to be explained and shown in the next demonstration.